So, having done reviews of atomic structure and the concept of the mole and molar mass, it's worthwhile pausing for a second before we continue, just to think about why we're doing all this. Chemistry, as a science, is the study of chemical reactions. It's how substances interact with one another to make new substances. A vital part of life, a vital part of modern industry. And the topic of stoichiometry, the mathematics of stoichiometry, because it is a very mathematical topic, but it is allowing us to make quantitative predictions. That's not sort of airy-fairy predictions. It's predictions with actual numbers, predictions that are able to be used in industry, in research, to find out and predict what's going on. The job of all sciences is to make predictions. It's to predict the future. And using stoichiometry in chemistry, we can make accurate predictions. If we know the masses of the reactants, the things that are going into the chemical reaction, it can tell us the masses of the products. If we're making gas, we can find out how much volume of gas is being made. And if we want to do a reaction in order to make a product in chemistry, then it allows us to match up the quantities of those reactants so that we're not wasting any, so that we have exactly the right amounts to react together, so that every atom finds its partner to create the reactants that we want to create, and there's nothing left over. So we're going to look at all of those concepts. Now, just a quick reminder that in the chemical reaction, we never make or destroy atoms. Okay? We might do that in nuclear physics, but in chemistry we don't. We are just rearranging them by breaking the bonds, by reforming the bonds into new configurations. This can be done in several ways. You can have smaller groups of atoms, molecules, atoms joining up to form bigger compounds. You can take bigger compounds and split them apart. Or more likely, you just kind of rearrange them into some new form. So let's look at an example. Sodium, a metal, reacts with hydrochloric acid to form sodium chloride, which is normal common salt, plus hydrogen, the simplest element, a gas at room temperatures and pressures. Now, in order to actually analyse in more detail what's happening, it's worthwhile looking in detail at the reaction, and to do that, let's just replace these with their chemical symbols. So, exactly what does sodium chloride include? What is hydrochloric acid in terms of the elements? And we have Na, the symbol for sodium, and that just sits there on its own. It's an atom. And joins with the compound hydrochloric acid, reacts with the compound hydrochloric acid, which is formed from one hydrogen atom and one chlorine atom, to form sodium chloride, which is one sodium atom and one chlorine atom, plus H for hydrogen. Okay, and you might look at that reaction and go, okay, that's a fair description. And you might go, and that's a balanced reaction. You've looked at reactions before, and you can balance reactions by counting the number of atoms on the left-hand side and the number of atoms on the right-hand side, and if they match, then you should be fine. Except that this is a bit of a problem in reality, because hydrogen atoms in the real world do not generally hang around on their own. Instead, hydrogen always forms a diatomic, a two-atom gas called H2. So if you have H2, then suddenly you don't have a balanced reaction anymore, because you've got two hydrogens on the right-hand side, but you've only got the one hydrogen, part of hydrochloric acid, on the left-hand side. So now we have to rebalance. So we have to have two HCl to provide the two hydrogens, but that gives us two chlorines. So we have two NaCl to use up the two chlorines, but now we've got two sodiums on the right-hand side, so we put two in front of the sodium on the left-hand side, and now we have a balanced reaction. Law of the conservation of mass tells us that all of the stuff on the left-hand side we have to have on the right-hand side. That's the balancing of the equation part. And now we have two sodiums on the left and two sodiums, part of the sodium chloride, on the right, two hydrogens and two chlorines from the hydrochloric acid, and the two chlorines going to the salt, and the two hydrogens buddy up and go off on their own as H2. So this is now a realistic description of what is happening. But those numbers, 2, 2, 2, they're not just kind of numbers, they're just used to balance the equation. We call these numbers, their technical name is stoichiometric coefficients, which is a very long word for a simple idea. And the idea is that is the number of moles, or the ratios of the number of moles of the reactants and the products. So we have, for every 2 moles of sodium, we will want 2 moles of hydrochloric acid to react together. If we had 3 moles of sodium and 2 moles of hydrochloric acid, we'd have some sodium left over. If we had 4 moles of sodium and 3 moles of hydrochloric acid, then it wouldn't work. Or could react would react, but there would be some stuff left over. Only if we have the same amount of sodium and hydrochloric acid, only if that ratio is 1 to 1, 2 to 2, whatever, the ratio is the same, then all of it will react. And you will get the same number of moles made, 2 moles of sodium chloride and 1 mole of hydrogen gas. So in terms of the number of things formed, you'll have half the number of hydrogen molecules formed as you'll have as sodium chloride molecules. Technically they're not molecules, it doesn't work like that, but sodium chloride structures. Okay, so 2 moles of sodium and 2 moles of hydrochloric acid will make 2 moles of salt, sodium chloride, and 1 mole of hydrogen gas. And this works if you substitute in the masses. We know the molecular mass of sodium, and we know the molecular mass of hydrochloric acid, that of hydrogen plus chlorine. We know the molecular mass of sodium chloride, and we can work out the molecular mass of hydrogen, H2. 2 lots of 2 times 1.008 is 2.016. And if we add these together, if we work it out, then we've got 45.98 grams of sodium, because we've got 2 moles of sodium in this example, plus 72.916 grams of hydrochloric acid, will make 116.88 grams of sodium chloride and 2.016 grams of hydrogen gas. And again, law of conservation of a mass, if you add up 45.98 and 72.916, you will get the same as 116.88 plus 2.016, in other words, about 19 grams. But of course, it can be a little bit confusing, this, because you don't have to have exactly that amount of sodium and hydrochloric acid, but you do have to have that ratio. It's all about the ratios of the substances. I think, for me, one way we can try and illustrate this is by using peanut butter cookies. So the ingredients of peanut butter cookies are that you need, now I looked this up, 240 grams of peanut butter, 100 grams of sugar, and 1 egg. And if you combine those all, it's like simple ingredients, simple molecules and atoms joining together to form one cookie. But except they don't form one cookie, because that will actually make 25 cookies. And if you don't want to make 25 cookies, or maybe if you don't have exactly that amount of peanut butter, or etc., then you can change the amount of peanut butter that you have. But if you do, you have to change the amount of sugar and the number of eggs in the same ratio. So if you want to, you can double the amount of peanut butter you use from 240 grams to 480 grams. But if you do so and you still want to make good cookies, you will also need to make double the amount of sugar, 200 grams, double the number of eggs, 2 eggs. You have to double everything. You have to keep the ratios the same, keep the proportions the same. And you will, of course, get double the number of cookies, which is always a good thing. As an exercise. Here's another equation, another substance. Lead 4 hydroxide. 4 is the sort of valence in this case, because lead has a couple of different ones. And sulfuric acid react as shown. So this is quite a complicated looking formula. Lead hydroxide is PbOH4, so you got these polyatomic ion of OH, you got 4 of those attached to each lead atom, plus sulfuric acid, so H2SO4, 2 hydrogens, 1 sulfur and 4 oxygens, so it's a big old molecule, You put those together and they will react to form lead sulfate, lead 4 sulfate, which is again 1 lead atom and 2 polyatomic SO4 ions, and water, H2O. If you want to make 1 mole of lead 4 sulfate, how many moles of sulfuric acid do you need? Well, again, it's all about the ratios. And the way to answer a question like this is to try to, first of all, make sure that you've balanced the equation. So balancing the equation isn't that hard, really. You've got, if I toggle between the two things here, let's just check it. On the right hand side you've got 2 sulfurs because you've got SO4, but you've got 2 lots of SO4, so that's 2 sulfurs. And on the left hand side you just have 1, so you can put a 2 here in front of the sulfuric acid, and that works fine because you got 2 sulfurs and you got 2 sulfurs, and now you've got 8 oxygens. 2 times 4 is 8, and you got 2 times 4, 8 oxygens there. Great. You've got 2H2 makes 4 hydrogens, and oh, that's not good. You got 2 hydrogens there. Okay, so how can you balance that out? Well, if you increase the number of hydrogens, and you've got and you've got the oxygen over here. So so you need to actually have 4 H2Os because you've got OH4, so 4 hydrogens here, so you need and 4 hydrogens here to give you 8 hydrogens. 4 oxygens times 2 is 8, that balances there, but you've got now the 4 oxygens over here, so again 4H2O takes care of those 4 oxygens, and you got the 1 lead, and you got the 1 lead, so that's fine. Check it if you don't believe me, look it up, but that is the balanced form of this equation. That means, if you remember from the previous example, that these stoichiometric coefficients tell you the number of moles you've got in and out. So in terms of reactants, 1 mole of lead hydroxide will combine with 2 moles of sulfuric acid to give you 1 mole of lead sulfate plus 4 moles of water. The question was to make 1 mole of lead 4 sulfate, how many moles of sulfuric acid do you need? Well, 1 mole of lead 4 sulfate is here. You will need, the answer is 2 moles of sulfuric acid for this reaction to work. 2 moles of sulfuric acid, 2 moles of sulfuric acid, and you will make, by the way, 4 moles of water. Okay, I think we'll just leave that example for a minute and we'll come back to the next one in a second.